So with this matrix, just as an example, let's say we wanted to take this matrix all the way to reduced row echelon form. What would be the operations we would do to do that? What would be some of the, or a good way to start turning this into reduced row echelon form?
You get everything below the first column to 0.
Yeah, because our first pivot, our first non-zero element in the first row is this 1 here. We want to use that to eliminate everything underneath. So what row operations would accomplish that?
You multiply row 1 by -4 and add it to row 2.
Yeah, so row 2, we're going to modify by adding -4 times row 1. And let's take this one step at a time. If we do that step, we're going to get first row unchanged. And what's our new second row?
The first one is 0.
Mhm.
And then it's -4 times 2, -10.
Right. And then
-7.
yeah. So that's our new second row. And let me keep the third row the same, Brad. So 1, 2, 3, 0, -10, -7, -3, 1, 1. What we've just done, that row operation can also be represented as a transformation matrix. There's a matrix that will do that same thing. In other words, if let's say we call this original matrix A, there's a matrix we can multiply matrix A by to turn it into this matrix. And to create that matrix, let's say we have our original matrix A. We want to multiply by a transformation matrix. To create that next step. If we wanted to build a matrix that does this, a matrix that keeps the first row the same, keeps the third row the same, but modifies the second row by adding -4 times the first row, how do you think we could build a matrix that will accomplish that?
For this one, do we do it like kind of in a general way and then find the coefficient?
Yeah, because we don't really have to care about what these rows were. If we think of this as just one column at a time, like this operation we're doing to the first column, we're taking the 4 from the second, from the second row of that first column and adding -4 times this value. In the second column, we're taking this -2 and adding -4 times this 2. In the third column, we're still doing the same thing. We're taking this second number and adding -4 times the first number. So we could think of this as just a single column. And let's say these values are A, B, and C. We want to multiply that by a transformation matrix. And we want the result to look like, what should the result look like if we're thinking of this as just a single column? If we did just this operation and that's it, what would this single column turn into?
Is it 0, -10, -7?
Well, not using the specific numbers, but if we just do this operation, because if you describe the operation we just did to get from here to here, What did we do to the first row? Ignoring everything else, from this first row to this first row, what have we done?
Nothing.
Nothing at all. We just kept it exactly the same. So we want a matrix that's going to take the first row and keep it exactly the same. What else about the matrix didn't change at all? Right, the third row. So we want a transformation that takes the original third row and keeps it exactly the same third row. So we want this third row, C, to stay the same, C. But we are changing the second row. Specifically, what did we do to the second row to modify it?
We added it to row 1 times -4.
Right. So if we do the same thing here, if we take the second row plus -4 times the first row, we take the second row plus -4 times the first row, and what does that look like? Yeah, B, or in this case, since we're subtracting, it'll be B minus 4A. So this is an overall description of the operation we just did. The row operation we just did is a row operation that turns A, B, C into A, B minus 4A, C. So no change at all to the first and third rows, but changing the second row by subtracting 4 times the first row. We're just doing that symbolically with A, B, and C as unknown constants, rather than entire rows of specific known numbers. Now, if we wanted to figure out a transformation matrix that accomplishes that, we can look at this one row at a time. We didn't change the first row at all. What's a row of a matrix that you would expect to not change the first row, the first value at all? Like if we look at this in terms of the first row, and I would think of this in terms of rows, because if you're multiplying a matrix times a matrix, you typically combine row and column. So if we're combining this row and this column, we'd be multiplying something times A plus something times B plus something times C. But what do we want the result to look like?
Just an A.
Yeah, just A. So what coefficients should we put in these 3 slots so we get just A and that's it?
1, 0, 0.
Right. If the first row of our transformation matrix is 1, 0, 0, then combining these, we get 1A plus nothing, and that's exactly what we want. So what should the second row be to create B minus 4A that we want? If we have 0, 1, 0, what's going to happen when we multiply this row by this column?
It would be B. It would end up being B.
Yeah, that would just be B, but we want B minus 4A. So the 1 here does give us 1B, but we also want minus 4A. So how do we accomplish that?
Oh, don't make it -4 instead of 0.
Yeah, if we put a -4 here, but we still have a 0 here because we don't want anything, any C contributed. Combining this row and this column, we get -4A plus 1B plus no C at all. And that's exactly what we want, -4A plus 1B and no C at all. And then what should the third row be if we want just C and that's it?
0, 0, 1.
Yeah. 0, 0, 1 will give us no A plus no B plus 1C, which is exactly what we want in the third row. So this would be our transformation matrix. We usually call that E for an elementary transformation matrix. elementary in the sense that it's just doing one simple operation and that's it. All it's doing is adding a multiple of a row to another row. It's just making one change. And that's often called, I think it's E sub 2(1), because we're talking about a change in the second row, first column. Or in the terms of the result, we're modifying the second row by using a value from the first row. But the important change happens in the second row, first column, which is where this -4 happens. Because apart from that -4, this matrix looks almost exactly like what important matrix? If that -4 wasn't there, what would we now have?
Diagonal.
Yeah, it would be a diagonal. Specifically, 1's on the main diagonal and 0's everywhere else. Have you seen that matrix before?
Yes.
What do we call that? It is in row reduced echelon form, but even more specifically than that, something very important happens if you multiply this by any matrix or vector. Like, let's say you multiply this by A, B, C. What would you get if you multiply this matrix times A, B, C?
BC.
Yeah, you just get A, B, C again. And because of that, because this matrix preserves the identity of whatever you multiply it by, we call this the identity matrix. The identity matrix times any matrix or vector doesn't change it. You just get the same matrix or vector back again. So this acts like what number? What number has this same property that you can multiply by anything and doesn't change it?
0.
If you multiply by 0, it does change it though. It changes it to 0. What multiplier won't change the number?
Oh, 1.
Yeah, this matrix, this identity matrix acts like the matrix version of the number 1. And we usually just call that a capital I. Or since it's 3 by 3, we say I sub 3. So I sub whatever means a whatever by whatever square matrix with 1's along the main diagonal and 0's everywhere else. And that has the unique property that if you multiply it by any appropriately sized matrix, the result is the same. It doesn't change it. So it acts like the number 1 as far as multiplication is concerned, but it's an entire matrix rather than just a number. The elementary transform matrix looks exactly like the identity matrix, but with just one change, representing that one modification that it does to whatever it's multiplied by. And this will work not only for a single column, but for an entire 3 by whatever matrix. If we take that same transformation matrix and multiply by our original matrix, 1, 2, 3, 4, -2, 5, -3, 1, 1, this has the effect of 1, 0, 0 means keep the first row the same. -4, 1, 0 means take the second row, but add -4 times the entire first row to get our modified second row. And 0, 0, 1 means take the third row and don't change it. So this operation, add -4 times row 1 to the second row, can be written as a matrix multiplier, an elementary transform matrix. Any questions on that so far? And another way, a couple other ways to think of this, you can think of each row of the elementary transform matrix as essentially like a recipe for building the new row of the result. Like 1, 0, 0, when you multiply these, like row and column, row and column, row and column, what does this 1 get multiplied by? Which specific numbers does this 1 multiply by in the second matrix? Yeah, the 1, the 2, and the 3. This 1 gets multiplied by everything from the entire top row. So you can interpret this as 1 times the entire top row, plus 0 times, what does this specific 0 get multiplied by?
The entire second row.
Yeah, 1 times the entire first row plus 0 times the entire second row. And then this 0 gets multiplied by the entire third row. So this row 1, 0, 0 means take the entire first row exactly as it is, plus no information from the second and third rows. That's your new first row. In other words, 1, 0, 0 in the first row means don't change the first row. Likewise, the third row, 0, 0, 1. That's nothing from the first row, nothing from the second row, and the third row exactly as is. So 0, 0, 1 means take the third row exactly as is and don't change it. But negative 4, 1, 0, what's this negative 4 getting multiplied by? Yeah, R1, the first row. And likewise, this 1 gets multiplied by the entire second row. So this negative 4, 1, 0, those instructions are saying multiply negative 4 times the first row and add it to the second row, take no information from the third row. That's your new second row. So this is a very useful way of interpreting an elementary transform matrix. Each row of the elementary transform matrix gives you instructions or a recipe on how to build the rows of the result, telling you how much of the first row plus how much of the second row plus how much of the third row to combine as a linear combination in order to build the new whatever that row is. Any questions on that so far?
I have a quick question. So
Mhm.
let's say it's the second row, the negative 4 times 1, negative 4, 1, 0. So then when we're multiplying it, it'll be negative 4 times the entire second row. How does that work
Well, since
again?
this is in the first position, like the first number in the row, that'll be multiplied by the entire first row.
Oh, it's like the entire row.
And you could look at this one at a time, like this row combined with this column.
Mhm.
You'd be multiplying negative 4 times the top number, plus 1 times the next number, plus 0 times the third number. But if you did that with the second row, you'd also take negative 4 times the top number, plus 1 times the middle number, plus 0 times the bottom number. So with each column, the negative 4 gets multiplied by the top number of each column. In other words, this negative 4 gets multiplied by everything in the first row. And likewise, this 1 gets multiplied by everything in the second row. And the 0 gets multiplied by everything in the third row. Any other questions on that so far? And one other way to look at the elementary transform matrix that's often useful, if we start with the identity matrix, just ones along the main diagonal and zeros everywhere else. That is a matrix that makes no change when multiplied. But what change do we want to happen? What's the operation we want to do to the original matrix? If we go back to the original change we made, we modified row 2 by adding negative 4 times row 1. If we do that same operation to the identity matrix, the same change we made, but we make that change to the identity matrix, that means we're not changing the first row. We're not changing the third row. But what does the second row become if we make exactly this change? It won't stay quite the same because we're taking 0, 1, 0, but what are we adding to it? What would negative 4 times row 1 look like here? Yeah, negative 4, 0, 0. So if we add -400 plus the second row 010. What do we get? Yeah, -410. So that's our new second row. And that's exactly the same as the elementary transform matrix that does that effect. So another way to build an elementary transform matrix, if you want a matrix that does some specific row operation, is to start with the identity matrix and apply the row operation you want it to do. The result is going to be the elementary transform matrix that does that row operation. Any questions on that so far? Then let's try out some more practice. I'm going to leave this example behind for now. And let's just try out some other operations that we might do with an elementary transform matrix. For example, let's say we wanted to build a matrix that takes an input of row 1, row 2, row 3. And doesn't actually change the numbers arithmetically, but just scrambles them around. Let's say we want to change that by swapping row 3 and row 2. So essentially we're doing a row swap here. We're taking the matrix, whatever these values are, and we're just swapping row 2 and row 3. Which is permitted as a row operation. In terms of a system of equations, this would just be equivalent to changing the order you write the equations. But what matrix multiplier would do that? What would be our transform matrix that causes the second and third rows to swap positions? And again, you could do this by thinking of it as a recipe in terms of what do you do to each row to build the new row, or you could also think of it as writing out the identity matrix and then making this change to it. So what do you think the transform matrix is going to be to make that happen?
Like for the first row, it will be 100.
Yeah, because what do we want to happen to the first row of the result?
The same.
Yeah, we want it to be the same. So this 100, we could interpret it as 1 times the first row plus nothing plus nothing. In other words, keep the first row and don't change it at all. But what are we doing to row 2 and row 3?
Row 2 would be 001.
Yeah, because if we interpret that as instructions or a recipe, this is saying take nothing from the first row plus nothing from the second row plus 1 times the third row. In other words, take the third row exactly as is, but in terms of position, put that as the new second row. And likewise, what should we write for the coefficients here?
010.
Right, 0, 1, 0. Again, in terms of instructions or a recipe, we're taking 0 times row 1 plus 1 times row 2 plus 0 times row 3. In other words, take row 2, 1 copy of row 2 exactly as it is, but we're putting that in the third position now. So this matrix has the effect of swapping rows 2 and row 2 and row 3. We would typically call this a permutation matrix. Permutation just means a way of ordering something, a way of scrambling things up. So this matrix has the effect of making a different permutation, a different ordering of the rows. We're keeping all the values the same, we're just scrambling up where they're put. Any questions on that matrix so far? And we could also look at this in terms of the identity matrix. If we start with the identity matrix, but swap rows 2 and row 3, there's what we get. So this is another way of building a transformation matrix. Start with the identity matrix, apply whatever operation you want to happen, and the result is the matrix that causes that transformation. Any questions on that so far? And one interesting property of a permutation matrix, let's say we call this permutation matrix P for permutation. If you apply this permutation matrix to, let's say this matrix, let's just call this A. You get a new matrix that's exactly like matrix A, but with row 2 and row 3 swapped. Let's call that matrix B. What happens if we apply the permutation matrix again? In other words, if we apply permutation matrix P to matrix B, what's going to happen?
Would be the original.
Yeah, you get back to the original matrix. Because if matrix P swaps row 2 and row 3, but then you swap row 2 and row 3 again, you get back to the original. And we could also write P times P, that could just be written as P squared. So a permutation matrix squared times any matrix A equals that same matrix A. What does that suggest about the matrix P squared? If you can multiply it by A and the result is just A, what does that tell you about P squared?
So 1.
If it were a number, it would be 1, but this isn't a number, it's a matrix. So what matrix acts like the number 1?
Identity matrix.
Right, P squared must be the identity matrix. And we can try that by actually multiplying it out. If we multiply P times itself, we can take each combination of row and column. So 1 times 1 plus nothing plus nothing. 1 times nothing plus nothing times nothing plus 1 times nothing. 0, 0, and 0. And then next row, if we combine second row, first column, we get 0 plus 0 plus 0. 0 plus 0 plus 1 times 1, so that's 1. 0 plus 0 plus 0. And then third row, combining the third row with each column. 0 plus 0 plus 0. 0 plus 0 plus 0. And 0 plus 1 times 1 plus 0. So we get back to the identity matrix. So this is an important property of any permutation matrix. If you have any permutation matrix that just swaps 2 rows, multiplying it by it twice, swaps 2 rows and then swaps them back. So any permutation matrix that just swaps 2 rows and that's it can be squared to get back to the identity matrix. That's a good way to check if anytime you've got an operation that essentially undoes itself, like applying it once makes some change, applying it again gets you back to the original. That means that the transformation matrix squared is going to be the identity matrix. Any other questions on permutations so far? Let me make one modification of that then. What if we have the matrix 0, 0, 1, 1, 0, 0, 0, 1, 0? if we applied that transformation matrix to some input vector, let's say A, B, C, and this doesn't have to be a single column. This could be any size matrix as long as it's 3 by something. But let's say we just treat each row as a single variable for now. What would the result look like?
Would it be like C A B?
Yeah. Because the first row says take the third value and put it in the first row. The second row says take the first value and put it in the second row. The third row says take the middle value, B, and put it in the third row. So this permutation matrix times the original vector is CAB. If we apply that same permutation matrix again, let's say we put CAB as our new input. So this same permutation matrix applied to CAB, does that get us back to the original? If you take like 001 CAB, what do you get?
B.
Because this first row
BA.
says take the third value, which in this case is B, and put it on top. The middle row says take which value?
C.
Yeah. This says take the first value, which is C, and put it in the middle row. And you could even see that by multiplying 1 times C plus 0 times A plus 0 times B is just C. And then this third row says do what?
The middle, so A.
Sorry, what was that?
A.
Yeah, that'll be A, because this 010 says take 1 times the middle number and nothing from the top or bottom. So CAB turns into BCA. Did that get us back to the original? Not in this case. P squared times ABC is not ABC, it is BCA. So this matrix, it does count as a permutation. All it's doing is rearranging the order of the terms. But it doesn't have the property that P squared equals the identity matrix. But what if we go one more time? If we permute again to get P cubed, that is doing the same permutation 3 times. Because we now know that P squared times ABC is BCA. If we try using that as our input, what do we get if we apply this same permutation to BCA?
We'd get A, B, C.
Yeah. So that means after 3 cycles, it does get us back to the original. That is ABC left multiplied by P 3 times, the same permutation 3 times, that it does get us back to the original. And A, B, and C could have been any values. So this suggests that P cubed is the identity matrix. So this permutation matrix that scrambles them in a different way takes 3 steps to cycle back to the same as the original. And the reason for this is if you take a look at what's happening to the terms in the vector, what happened to this A? Where did it get put?
Second row.
Yeah. The first row, the A, got moved to the second row. And then what happened to the B?
The last row.
Right, the B gets pushed down to the last row. And meanwhile, what happened to this C?
The first row.
Yeah, that gets shoved up to the first row. So this is not a simple row swap. You're not just taking two rows and making them change places like we did before. If that was the case, if all you're doing is swapping the place of two rows, then swapping them again gets you back to the original. So P squared would be the identity matrix. But this is not a simple single row swap. This is more of a shuffle. We're moving everything down, and then the one that just dropped at the bottom gets pushed up to the top. So A, B, C, everything moves down. The one that fell at the bottom gets pushed up to the top. Do that again, push everything down. C goes down, A goes down, B falls out the bottom, gets pushed up to the top. We haven't gotten back to the original yet. But same process again. C goes down, B goes down, A falls out the bottom, gets pushed back up to the top. Now we're back to the original. So any permutation, any method of rearranging the rows, if you repeat it enough times, you will eventually cycle back to the original. It just may take more steps depending on how complicated the permutation is. For a 3x1 vector, if you just have 3 rows to care about, or a 3 by anything matrix, the only ways you can really do a permutation are swap 2 rows, or move everything down and the bottom falls up to the top, or move everything up and the top falls down to the bottom. So everything is going to be either a row swap that takes 2 steps to cycle, or a push down or push up that takes 3 steps to cycle. But if you're dealing with a 4 by something matrix or larger, there are even more ways to permute the rows. So it becomes more and more complicated in terms of possibilities. But no matter how complicated the permutation is, if you repeat it enough times, you'll cycle back to the original. This even applies to much larger and more complicated situations. Like for instance, if you've got a deck of cards and you're shuffling the cards, if you're shuffling the cards the same way every time, like the same way of rearranging the cards, if you shuffle it enough times, you'll eventually get back to the original order of the deck of cards, if you're doing the exact same shuffle over and over again. Because a particular shuffle, a particular way of shuffling a deck of cards is just a permutation matrix. You're just using a certain procedure of rearranging the deck of cards. If you apply that exact same procedure over and over again, you will eventually get back to the original stack, the original order of the deck of cards. It may just take a very, very, very large number of shuffles. But any permutation matrix has the property that P to some power will eventually be the identity matrix. It just varies how many times you have to multiply it by itself. Any other questions on the permutation matrix idea? Then let's try one more quick example, since we've got a couple of minutes left. Let's say we had a transformation matrix that looks like this. Let's do a 4x4. So this is not what I would call an elementary transform matrix. This is a much more complicated transformation than just one single change. But we can still use the same idea of looking at what it's doing to the input. Let's say our input is A, B, C, D. And each of these variables could be interpreted as a single number or could be interpreted as an entire row of some larger matrix. The same procedure still applies. If you think of this as a operation that's being done, we could call it, let's say this is a transformation matrix T, and we're applying it to a vector that could be thought of as an input. Let's say we call this vector X. So T is an operation, a transformation. Being applied to an input vector. And we want to create an output vector. Let's call that Y for now. So this is essentially a function. It takes a vector as input, gives you a new vector as output. And we could do this by multiplying it out, combining row and column, and so on. But instead of combining row and column as usual, let's look at this in terms of instructions or a recipe. What is this entire first row saying to do?
The first input.
Yeah, we're taking the first value of the input because this 1 means take the entire first number exactly as it is. And then 0, 0, 0 means take no information at all from the others. So the top number will still just be A. What is this second row saying to do in terms of a recipe for building the new second row?
Swap C and B.
It's not quite a swap though, because this 0, 0, 1, 0, this is just saying what you do to build the new second row. So the 0, the 1, and the 0, that's saying take what information from our input matrix?
C.
Yeah, we're taking just C because we got nothing from the first row, nothing from the second row. We're taking the third row exactly as is, that's C, and nothing from the fourth row. And since this is the second row of the transformation, that's going to produce the second row of the result. Just C, that's it. And then the third row, note that this is not saying just take B as it is. So this is technically not a permutation. We're not just swapping rows. We are genuinely making other changes. 3, 0, 1, -2. What is this saying to do?
Three A.
Right, we're taking 3 times the entire first row, which in this case is just A. And what are we combining that with?
Plus C minus 2D.
Right, 3 times the entire first row, no information from the second row, the third row exactly as it is, and -2 times the fourth row. And then what does the fourth row of the transformation say to do?
Or C plus D.
Yeah, we're taking no information from the first 2 rows because of these 2 zeros. We're taking 4 times the third row and combining it with this fourth row exactly as is. So 4C plus 2D. And we're looking at this as just a single column as input. We could use an entire column, an entire matrix as input, and just apply this process to each column. So we'd be taking, for instance, the entire first row, the entire third row, 3 times the first row plus 1 times the third row minus 2 times the fourth row, and so on. So this would be the output. And this is not just an elementary transform. This is multiple changes, a more complicated transformation. And one important thing to note here, what doesn't show up in this final result at all? Yeah, the value of B does not influence the result, which means we have lost information. The fact that this column is all zeros means B is always getting multiplied by 0. So whatever B is doesn't show up at all in the final result. Everything else you could reverse engineer. Like if you didn't know what the input matrix, input vector was, but if you know the transformation matrix and the result, you could reverse engineer this and find the values of A, C, and D. But there's no way you could figure out what the value of B was because B does not influence the final result. And that tells us that this transformation is not invertible. You cannot undo it. Like if I just tell you the result, there's no way you could figure out entirely what the input was because you have no information about B. So this would be a non-invertible transform. Any other questions on that?
For the last row, is it 4C plus D?
Oh, yeah, I forgot about that. I was looking at the 2 from above.
Mhm.
So yeah, just 4C plus 1D. Any other questions? All right, then I will see you next time.
Thank you.
You're welcome.